So today we'll be solving the seventh question of the book Challenges and Thrills of Pre-College Mathematics of exercise 2.1. So the question says that if Sn is 3 plus root 5 whole power n plus 3 minus root 5 whole power n, show that Sn plus 1 is equal to 6 Sn minus 4 Sn minus 1, and that Sn is an integer for all n belonging to natural numbers. We also have to deduce that the next integer greater than 3 plus root 5 power n is divisible by 2 to the power n. So for the first subpart of the question, let's just take 3 plus root 5 and 3 minus root 5, right? We also see 6 and 4 here. When we add 3 plus root 5 and 3 minus root 5, that is 3 plus root 5 plus 3 minus root 5, we get 6. And when we multiply them, 3 plus root 5 multiplied by 3 plus root 5 is equal to 3 square minus root 5 whole square, which is equal to 9 minus 5, which is equal to 4. So their multiplication is 4 and their summation is 6, right? So what we can say is that if we have the quadratic equation x squared minus 6x plus 4 is equal to 0, if this is the equation, then the roots of this equation are essentially 3 plus root 5 and 3 minus root 5, right? Now, in this equation, if we multiply each side by x power n minus 2, right? Or, yeah, let's just multiply both the sides by x power n minus 2. So what we get is x power n minus 6 x power n minus 1 plus 4 x power n minus 2 is equal to 0, right? And since the roots of this equation are 3 plus root 5 and 3 minus root 5. Both 3 plus root 5 and 3 minus root 5 satisfy this equation. That is, 3 plus root 5 power n minus 6 into 3 plus root 5 power n minus 1 plus 4 into 3 plus root 5 power n minus 2 is equal to 0. If we take the term that is multiplied by 6 and 4 to the other side, we get 3 plus root 5 power n is equal to 6 into 3 plus root 5 power n minus 1 minus 4 into 3 plus root 5 power n minus 2. Right, this is what we get. Let's call this equation number 1. Right? Now similarly, since 3 minus root 5 power n is also 3 minus root 5 is also a root of the equation, it will also satisfy the same condition. So we can just write 3 minus root 5 whole power n is equal to 6 into 3 plus, sorry, 3 minus root 5 power n minus 1 minus 4 into 3 minus root 5 power n minus 2. This is equation number 2, right? And here n is any natural number, right? Because essentially you're just multiplying by n minus 2. So it can be, I mean, so long as n minus 2 is greater than 1 or 0 for that matter. So when we add both equations 1 and 2, we get 3 plus root 5 whole power n plus 3 minus root 5 whole power n is equal to 6 into, we'll just take the 6 common, so we get 3 plus root 5 power n minus 1 plus 3 minus root 5 power n minus 1. Then we take the 4 common in subtraction, so we get 3 plus root 5 power n minus 2 plus 3 minus root 5 power n minus 2. But we know that this term here is essentially Sn is equal to 6 into, this term here is essentially Sn minus 1, and this term here is essentially Sn minus 2, so minus 4 into Sn minus 2. So we have, if we just increase n by 1, we can write this as Sn plus 1 is equal to 6 Sn minus 4 Sn minus 1, which is exactly what we needed to prove, right? So this is the first part done, right? Now for the second part, what we need to prove is that Sn is an integer for all n belonging to natural numbers, right? So now we'll prove this by induction. So base case, we take n equal to 1, right? So when n equal to 1, we have um, S1 is equal to 3 plus root 5 power 1, so it's just that, plus 3 minus root 5, which is equal to 6, which is an integer. So this is, the base case is true. Now for the inductive hypothesis, let's say Sn is an integer for all natural numbers n less than k plus 1, right? So since it is an integer for all natural numbers n less than k plus 1, we can substitute n equal to k. So we have sk is an integer, and also since k minus 1 is less than k plus 1, we can also say that sk minus 1 is an integer, right? And from the previous part, we know that Sn plus 1 is equal to 6 Sn minus 4 Sn minus 1. So instead of n, we just substitute k. So we get Sk plus 1 is equal to 6 Sk minus 4 Sk minus 1, right? Since Sk minus 1 is an integer, this is an integer. And since sk is also an integer, and since the only operations being done here are multiplication and subtraction, sk plus 1 must also be an integer. So we have proved that if um, all Sn's are integers for all natural numbers n less than k plus 1, then it is also an integer for sk plus 1, and hence by principle of mathematical induction, um, Sn must be an integer for all natural numbers n. So that's the second subpart that we solved. Now we need to reduce that the next integer greater than 3 plus root 5 whole power n is divisible by 2 power n. Now we know that Sn, Sn is always an integer for all natural numbers n. And Sn is essentially 3 plus root 5 whole power n plus 3 minus root 5 whole power n. Now, if you calculate root 5, you'll get its value to be 2.0 some decimal number, right? And 3 minus root 5, 3 minus root 5 will essentially be 0 point some number, which will be less than 1, right? And so when we um, take the power of whatever number to the power any natural number n, it will always be less than 1, as if you have some number x to the power n, where x is less than 1, then x power n will also be less than 1, right? So suppose 3 plus root 5 whole power n is some number, let's say a. This is the integer part of the number, and decimal part is say b, right? So we'll write it as a dot b, and then plus we have 3 minus root 5 whole power n. This is also always less than 1. So let's say this is 0 point c, right? Where c is some number after the decimal point. So essentially, when we have this is equal to Sn, which is always an integer, right? And if we have a dot b plus 0 dot c, essentially this always has, if it's an integer, this always becomes a plus 1, because it, let's say it doesn't become a plus 1, if it becomes a plus 2, then this 0 point c has to be greater than 1, but this is not possible because it is always less than 1. So, and since we're adding a positive value, since 3 minus root 5 is positive, and we're adding a positive value to already a decimal number that is greater than a or equal to a. So this value cannot be a. So essentially this will be a plus 1, right? And this is always an integer. So the integer that is greater than 3 plus root 5 power n, the integer, sorry, here, integer greater than root 5 power n is essentially equal to Sn, because this is essentially the next number after 3, the next integer after 3 plus root 5 whole power n, because this is only a fraction, this is less than 1, right? So essentially what the question boils down to is that we need to prove that Sn is divisible by 2 power n for all natural numbers n, right? So we'll again prove this by induction. So we have base case n equal to 1. We have S1 is equal to 6. We already saw that above, which is obviously divisible by 2, as, yeah, 6 divided by 2 is equal to 3. So this is obviously correct, right? Now for the induction hypothesis, let's just say that Sn is divisible by 2 to the power n for all natural numbers n less than k plus 1, right? And we also have Sn plus 1 is equal to 6, Sn minus 4, Sn minus 1, right? So let's substitute n equal to k. So we have Sk plus 1 is equal to 6, Sk minus 4, Sk minus 1. Since Sk is divisible by 2 power k, and Sk minus 1 is divisible by 2 power k minus 1, we can write this as 6 into 2 power k into mk, where mk is some integer, minus 4 into 2 to the power k minus 1 into mk minus 1, where mk minus 1 is an integer, is equal to Sk plus 1, which is equal to, we can take the 2 from the 6 here, so you get 2 to the power k plus 1 into 3mk, and from here also we get 2 to the power k plus 1, so minus mk minus 1, since we took 2 to the power k plus 1 common, is Sk plus 1. And This part 3 into mk minus mk minus 1 will be an integer since mk and mk minus 1 are integers and only the operations being done are multiplication and subtraction. So essentially what this means is sk plus 1 is divisible by 2 power k plus 1. And this proves the inductive step, and hence by principle of mathematical induction, we can say that Sn is divisible by 2 to the power n for all natural numbers n.